Good afternoon. Thanks for giving me the opportunity to give the talk. So I will discuss the SmartCut process for ECSEL SiC. We call it SmartSiC. That's a development done in Soitec and supported by the Doctoral program, of course, with all the partners of the program. And the agenda of the talk will be, very briefly, the system motivations. We are all convinced that you need to have good SiC materials for many applications. Then what is the total specific affordable first to the SmartSiC? So few words on the SmartCut process itself. Then more in details, material engineering. We have poly-SiC, turning mono-SiC, but we have poly-SiC, but also resistive. We have some specificity to the bonded wafers, which are the HTIs, to take care. And also some specificities to the SmartSiC, picks up mono satellite. It's a composite wafers, and so we take care of the methodology. Last but not least, some data on 6-inch wafers, which are on the way to insert clarifications, on 200 millimeters wafers, which are now demonstrated and engaged in something. So we all know that we are growing demand for SiC in many applications, from 600 volt to many kilovolt. So many applications request some SiC, and during the last decades, we have continuously improved on the SiC material. We increase the size of the wafers. Now with 200 millimeters, even if I heard yesterday it's for them 3 events. NPD micropipe density is continuously improved. We watched also yesterday some data 0.11 NPD defect at 5 centimeters. If you discuss specifications like the people. And of course, a strong forecast for a lot of demand, mostly driven by the electrical vehicles. And 2045 in Europe, where we all buy some electrical vehicles. We still have some challenge to facilitate the SiC adoptions. We need to take care of the quality and reliability. In SiC, we have some defects, impact the device yield. So at the end, the cost. So if we can cure some defect, avoid some defect from the materials, so SiC taxi, of course it's welcome. We need also to take care of the cost, the final cost, whose studies from extraordinary survey first cost, the practice cost, and at the end, first about the cost. And so, of course, if we can improve the cost of ownership of the total solutions, is better. Last but not least, 200 millimeters. 200 millimeters, everybody choose the 200 millimeters essential. So we want to buy some 200 millimeters, sometimes launch. So if we can accelerate the 200 millimeters at a point start, so at the increase in the availability of the materials of the market, it will be also welcome. So what do we propose as SmartSiC is, I say it's not about only about, it's kind of composite materials. We associate in so-called SmartSiC performance generations a prime quality single crystal mono-SiC, thin layer of one SiC on top of ultra low resistive or ultra high conductive SiC materials, a poly-SiC. Here we have mono-SiC, YESvGaN to support the repeat axis, the electricals. Below, we have poly-SiC in less than 5 micrometers, and we will see one with the almost 2 to 3 micrometers, so we divide by 10 and we still serve the time. And how do we, what is the position of the material in the chain? That's the conventional position for Soitec. We are buying some bulk materials. It can be SiC, can be silicon carbide. We are doing some engineering substrates. Then we sell these engineering substrates to foundry device makers, or at the end we obtain the product. So we are part of the value chain. For SOI, which we are also built, and now says. So a few words about the SmartCut process. A SmartSiC wafer, as we apply the SmartCut process to ECSEL methods. So we have typically, we posted two wafers, the donor wafers and bundle wafers. The donor wafers, like that, as I mentioned before, that's the prime quality low resistivity. The bundle wafers is a low resistivity polySiC. In both cases, we begin with surface degradations to be able to hold the wafers on surface degradations, typically low this appropriate roughness performance. After a smart cutting plant, here to define the thin layers we consider with hydrogen payload compound, we will have a conductive bonding process, and then we'll take a kind of sandwich, where we go to the splitting process, that's a low temperature early process. During the splitting process, we have a cleavage on the hydrogen included layers. So we separate these bonding pairs in two parts. One part in the SmartSiC, only plus a thin layer of monoxide. These SmartSiC wafers will continue in the line, a finishing process which includes snapping into a high temperature annealing, squad at the end, and PP ready surface. Second part after the splitting, we call it the negative, so that's a piece of the materials of the mold recession is then refresh and obtain a new donor wafers. So with the refresh cycle, set of course the skin focus, and we from one donor, we will have 10 SmartCut wafers. So we multiply the number of wafers. The refresh of photo affinity. The refresh is well known in SmartSiC technology. We apply within SmartSiC with very high number of research per donors. The benefit when we talk about green electronics, at the beginning we have a donors for the wafer SiC or materials coming from a PVT ball, balls of the SiC needs to grow at very high temperature during a very long time, and typically from the ball we obtain 40, 50 monoxide work. With the refresh, we take the same number of donor wafers, we associate with the poly-SiC made by CVD, quite lower temperatures, shorter times to prepare, quite usually chemistry also, and we refresh, and so with one ball we create 500 SmartSiC wafers. So we reduce, we multiply the number of wafers from each ball, and we of course save some energy, save some CO2 emissions per wafers. Okay, we have another wafers, we have another wafers. We need to bond. We need to have conductive bonding. We of course have several options to do some bonding. One option could be the direct bonding, one is the surface activation bonding, the last one actually is the bondings. So we should do direct bondings. It's quite difficult because you always have some oxide on the surface. It doesn't work. Surface activation bondings, when you have the reagents, then can have bonding. Okay, you have no oxide, so you can have some bonding. You can have more defect at the bonding. But it's very, very sensitive to the environment and the conduction is not so good. We adopt an atomic diffusion bonding process when we deposit thin layers of silicon, and when we bond both, and we have a good bonding place, and the bonding production. If you cut a bonding interface, we obtain absolutely no laminations. We have a fully standard interface on these 10 pictures. You can see here we have the mono-SiC thin layers. Here you have the poly-SiC. We rely on just a small bonding interface. How do we monitor the quality of the bond? Of course, we do the layer we transfer, that's below microscopic defect, and no microscopic defect, and then some of the key performance that are the electrical conductivity. Electrical conductivity is measured with dedicated methodology related from studies where we generate and test structures, and then we measure the current flow through different conditions, and we confirm that we have an cubic behaviors of the body statistics. We confirm that we already see less than 0.1 million square centimeters. And of course, if we associate this very low instability of the body effects plus the very low ultra-low modicity of the polysection, we have a strong resistance index that we compare with conventional wafer systems. We could also check for the bonding interface if we have thermal conductivity. The person who would add thermal barrier to be a problem, especially for short circuit. So just here a slide which will be shown by my colleagues, Alex in the next ICS hearing conference. We do with some colleagues, then some time dependence, thermal resistivity measurements. And we can see that we have more thermal barrier at the domain. Well, we transfer, we have a SmartSiC after the splittings. We need to finish. The finishing is some SiC. We need to have long resistivity to be EMPIR. During the development phase of the SmartSiC, we have a quite interesting improvement on the workplace. And now, with the current vintage, we obtain such kind of mapping with the RMS less than 1 constraints. Full compatible Ghent and as good as the models. We demonstrate that this final surface, the SmartSiC programs, is compatible with LED. We can make some epitaxy. And epitaxy with judge and its partners, kind of preference. I confirm that the possible effect can take bigger with the result after EPIN. And we can do also internally now some tests, and if we also spend up to 30 microns, we obtain, I think, pretty good results in time or possibly. Well, we are SmartSiC. We need to have, of course, do some analysis. PolySiC is obtained with playback by the CVD technology. But PolySiC CVD, you can have a very large choice of microstructures. Of course, here I show a few examples. Of course, some of these options can be considered for the SmartSiC. But so now we have the most stable potential CVD process at certain temperatures on which we can prepare some polySiC wafers 6-inch, 8-inch. One of the key points is the electrical instability. As I mentioned, specification is less than 5 million components. Typical performance in the range of 10 centimeters. So we divide by 10. There's some typical instability of the type versus the model. And we can apply the same process and can obtain the same performance, whatever the result 6-inch per 8-inch. We also have some other benefits of the PolySiC. Here are just pictures shown during the last HCS countdowns that during those. First is some benefit of the flatness. So lower flatness will open some minutes for the buffer process. And also we know that it could be a concept for circuit boards, a stable voltage when we are doing some backside dynamics at the end of the device. And we achieve in appropriate backside dynamic some voltage which is stable or sometimes even better mixer of monoxide. Of course, we need to adapt to the process because we are losing hiding or polycystic melting noises. So we could have some high voltage depending of the backgrinding process we have done. So with an appropriate backgrinding process, especially if we remove all the stress coming from the surface after the backgrinding process, we can have a voltage in the same range or even better. So, two specific points. And the first one is we are doing SmartCut, so we are bonding two wafers, so the wafers are round shape. So after the process, we have a TLX. That's related to the SmartCut bonding. It's happened also for all the collectors. So the point is we need to monitor and we can move that. Principle is you bond two round shape wafers also at the extreme edge dose. Even that knows we can tweak this data. So you always have the SmartSiC wafers and the weeks here, which is where you see the process. One question we have also is how does the edge trace move, change during the process? It's stable. So just to share here some pictures of the edge trace after the different processes in O line and during the epitaxy cell, somewhere in the edge separation. Here's some pictures. After the splitting, after annealing, after CMP, add with the reverse, and after epitaxy. Exactly the same prediction. So you can observe, yes, we can add some, here we have an edge shape, an edge trace. Sometimes we can add some local variation of the edge trace, depending on the local variety of the edge shape, either donor or on the weapons. But it does not move during the process. It's fully stable. We can have more focus on the behaviors of the trace before or after the epitaxy. So we do here the same inspections after the EP. We see we have more denominations. We see also if we compare before and after EP, but we have no variations. The signature you obtain it and find exactly the same. So not to lose any materials. You have a full stable exchange.
Okay.
We also checked by the cross type of the YESvGaN, but the polycrystalline material to skin is not faster version of the monoxide. So here, of course, here is the edge of the SmartSiC. Here is the handle for XLC. Here we add at the beginning the monoxide of layers. After the TP, we growth and monoxide layers. 6, 10 microns. Here we go polycrystalline. So no issue on this side. And what is the width of the edge trace? The width of the edge trace is related to the edge shape of the donor wafers of the other wafers. So it's related to the wafering of each wafers. It's also related of the bonding and the splitting process. So we need to consider both with the substrate formulation and the process formulation. Today, in Soitec, we have an ECSEL JU that's fighting with corresponding methodology. So we guarantee the 5 nanometers of edge width. The target is to be at less than 3 nanometers by end of the year. As on the pictures I show here for the product vintage of the beginning, we are quite confident that we will succeed in this target, and we already think how to go beyond or continue to reduce the extra noise. Few words on the methodology. Again, SmartSiC is not the monoxide. It's not the monoxide, pure monoxide. So we need to adjust the methodology because we have a thin layer of water on an opaque on those wafers. So we are using many methodology tools to ensure the material quality. We are checking, of course, for the transfer layers at the microscopic scale, so just to be very questions. The transfer layer defectivity at the microscopic scale, and I will go more deeper on this part. We also check for the geometry of the wafers, of the transfer layer thickness, but also have some samplings for different contaminations, bonding interface and CT, electrical relativity of materials, crystal quality. All you start the evaluations of discipline, so it's not some. Other characterization on the top of the tables here are 100%. That's part of a commitment to monitor the material delivered. Regarding the transfer surface defectivity, micro defectivity, today we are measuring with Defect tools. Tomorrow, HVM line, it will be with the caretaker SPA2. And then line the open end of the tunnel, so it's very makes. For SmartSiC inspections, defect professions, we want to divide the defect in three main types. The first one are the crystal defect, when after we go to the pure SmartCut defect in the surface, and the surface has particular actions. The crystal defect, yesterday we discussed about all the crystal defects we can have in a SmartSiC wafer, in the mono-SiC wafers, like opite, ESD, EPD, weight inclusion, and so on. Mostly, the main point is this crystal defect and transfer from the mono-SiC. The SmartCut doesn't change the crystal quality of the transfer medium. We just take the crystal quality of the donor, we obtain exactly the same on the wafer. Again, the pictures, we published it in tour in ICS here in 2021. Here we compare with the average characterizations. The crystal of the SmartSiC wafers versus the same crystal from the donor, the same dose at the same position, and we can observe exactly the same defect at the same positions. So when we have a certain density of KDT JU on the donor, we have exactly the same on the Gen1.2. When we have a certain density on the substrates, we have the same on the Gen1.2. Second point is, I would say that what we call the SmartSiC data. So the current detections now is the SiC. Just a reminder again, the SmartSiC substrates are opaque due to the polarization. So we just need to adjust the SiC recipe. The reflectivity is different. So, but we just, if we consider a mono-SiC bulk setting that the SiC we apply, we set more on the SmartSiC wafer, we have a full saturation and all the measurements. So we just need to adjust few parameters. And then, we measure, and after measurements, we observe some defect, and we can classify this with 20 defect classifications. That's in place, what can we use? And we have three main kind of this. The first one is a so-called void. A void, something like that. It's more than micron. It's an open defect. Black part of the void is like a pooling section in the bottom or the bottom of this. We have some missing materials. It's not from the SmartCut process. Can be extent. Here we have a bubble. A bubble is smaller. It's partially open or closed defect. It could generate a void sometimes. It's also coming from the SmartCut cases. And what we call the crystal originated defects, the crystal originated defect, it's an area. Again, an open defect, mostly related to the top crystal defect. A micropile on the very succeeded on wafer. That's a small void. At the end, it gives a crystal contains that's the bulk carbon units leads to a slope. We will have a posters, my colleagues in Casella, we will have a poster on the subject, so I advise you to listen with her in Sorrento in 2 weeks. We have quite good correlations between the donor mono ECSEL wafers defect and the finished SmartSiC defect. If we consider one donor pixel, one donor wafers, here the measures of the crystal defect on the donors, we keep only the micropipe, and if you measure the same SmartSiC wafers obtained with this donor, for the quality you have to obtain quality correlations. 1 micropipe, 100% used in defect one. Of course, we will also show also the detect and the buildings. We improve the defect density. Here a graph, SmartSiC defect density as measured by the SiC from quarter to quarter. We observe quite nice improvement, I think. And today's specification is there, 0.5 is a percent yourself and capability in terms of 0.1, 0.6. We sometimes reduce the contribution of the donor wafers. Second, we improve the SmartCut process with surface fabrication before the bonding. All the donor, under the number. We will continue, of course. But now, as I mentioned before, we have 3 waiting sources. We have 3 waiting classification of defect. Bubble voids and crystal originated. But some defect coming from the SmartCut, some defect coming from the donors. And hopefully we have 50% just to cover some of the lesson of coming from the more recently 50% from the SmartCut test. Last but not least, we have the crystal, we have the SmartCut defect. We need to take care of the surface eagles, the micro scratch. This is something which is difficult to observe with the SiC. So that's the reason why we move in the common mounts to SPA2. So SPA2 will open a path for low threshold inspections. So for the moment, as I mentioned before, we are doing SiC with most specifications. In the coming months, we will have SPA2 where we will sort between non-tunable defect, tunable defect, actual threshold on micro scratch. We have some first data. If you compare the SiC mark on the same measurements with the SPA2, we have more defect. So of course it helps us to continue the roadmap and to continue to improve the start supply. Okay, few data now on 6-inch. First, the pictures, like what is the SmartSiC wafer. Second, as I mentioned before, from quarter to quarter, surface quality improvement. So a defect, a wafer with 0.1 defect at 4 centimeters, and now the capability is in the range of 0.60. The layer we transfer 600 millimeters of mono ECSEL with the fitness controls on the web at 0.1 millimeters. With typical distribution related to the PowerElec. The geometry is driven by the earlier wafers. They have been by something which is quite standard for the SmartCut process. The geometry of the SmartCut engineering wafer is driven by the earlier wafers. So the geometry is driven by the earlier wafers, the poly-ECSEL. So we have no contribution of the transfer layers. On the electrical performance, we demonstrate some new alloy resistivity. We have some full mappings which confirm that it's quite stable on the whole worker surface. We also confirm that the electrical performance is stable from room temperatures to the device operating temperatures. Same performance up to 175 degrees. So we can optimize the resistance. Of course, we can consider the benefit of such resistance if we do some time binding. If we compare the mono ECSEL performance versus the SmartSiC, of course, we have a strong improvement Also it's better for 250 records. But even if we reduce the work of course, the bargaining to we have something. Okay. Last point, 200 millimeters. So now the 200 millimeters also have been demonstrated. Again, the pictures from last year, it was one of the first workouts for great transfer quality. And we have really important the last year from the some initial levels on the transfer layer quality as measured with YESvGaN. We have the chain of the 6 or 8 inch perspectives in the convertible dimensions. And so we can benefit of the development in 6 inch to 200 millimeters. So we demonstrate now some very similar performance. And we deliver the first prototype and obtain already drawing 0.1 decibels of makers, big for 1 year. Again, pictures on the electrical performance, poster from our CLAT colleagues to be shared to the colleagues in the YESvGaN on the bonding interface mapping on 200 millimeters wafers. Again, quite homogeneous, only very good bonding interface making, same performance time. So to conclude, the SmartSiC engineering is a substrate on the path to industrialization, qualification, ultra-low electrical resistivity, improvement of the shutter resistivity, 6 inch now entering qualifications, 200 millimeters in sampling, on an industrial fab opening end of September. Here are pictures, but while the drawing of the architects were in Soitec, we have the main fab for the SOI, Berlin 1, Berlin 2 here. Berlin 3 is devoted to POI, and Berlin 4 will be for 2,500 square meters of scale for the SiC operations. And I should have pictures. Now the fab is built on the tool ordering with schedule on RS on the first quarter end of September. Thank you.